We've looked at the double Riemann integral over rectangles. Now let's do double integration over general regions. So take a second to look at these three pictures and decide what they have in common and where their differences lie. For this first picture on the left, if I wanted to describe the region here that we would integrate over, so this is like a domain for integration, one remark I would make is that all of the x values are situated between two fixed numbers. Say a on the left and b on the right. And then y values in this region are passing from a curve on the bottom to a curve on the top. The curve on the bottom can be treated as a function of the form y equals g of x, and the curve on the top, y equals h of x. For the picture in the middle, the roles are reversed. Here it's easiest to say that the y values are bounded between two constants. Let's call them c and d. And then x values go from the curve on the left to the curve on the right. I'll describe the curve on the left as x equals m of y, and the curve on the right, x equals n of y. Similar situations, just different roles for the variables. The one on the left is what we'll call a type 1 region. And it's a region you can describe as x is bound between two constants, and y is bound between two functions of x. The middle one is what we'll call a type 2 region. For this type of region, we'll say that y is bound between two constants, and x is bound between two functions of y. Now, if we look at the picture on the right, we could interpret this shape as either type 1 or type 2. So you could either say that x is bound between a and b, and y is going from this constant value down here up to this line. Or you could say that y is bound between its lower bound and its upper bound, and x is traveling from this vertical line to this other line. So this one is called a type 3 region, and basically it means it's both type 1 and type 2. So if I wanted to integrate over a region that looked like one of these three pictures, the first thing I want to do is understand how to describe the bounds on the variables. So if the region was type 3, you would choose to either describe it as a type 1 or type 2 domain. I want to take a couple minutes to define Riemann integration over a general region like these three. This is going to be a quick demonstration because once we actually start integrating, we won't really return to the notions I'm about to introduce. But say that I want to integrate over this domain D in the xy plane. This is an irregularly shaped domain. It's not a rectangle. Here's the graph of my function over D. So every point on this graph has the form x, y, f of x and y, where x and y belong to this strange domain D. Riemann integration was defined over rectangles. So what we do is we take our domain and we enclose it in a rectangle, just like the ones that we saw before. We then extend our function by setting it to be 0 outside of D. So I declare that the value of my function outside of the original domain is 0. Now it makes sense to compute the volume enclosed between the graph of this function and this rectangular domain. We won't pick up any positive or negative volume outside of the original domain. And then whatever the volume we pick up over the original domain comes out to be, that's what we would say is the double integral of this function over the domain D that we started with. So if we suppose that f is continuous on some region D, we extend f outside of D by saying it's the way it started if x and y belong to D, and it's 0 outside of the original domain D. Then technically the definition of the double integral of f over D, to make it precise with Riemann integration, it's the double integral over R of the extension of f dA. Now in practice, here's how we actually do this. For a type 1 region like the one we have on the left, the double integral is not going to pick up any volume outside of d. So when we integrate it, what we're going to end up doing is an iterated integral where the outside bounds are those for x, because x is bounded between a and b. And then the inner bounds are going to be the ones for y. Y goes from g of x to h of x. So instead of integrating over a rectangle, the inside bounds indicate that y is bounded between two functions. So this would be a type 1 integration. For type 2, it's similar except the roles of the variables are switched. So our outside integration goes from c to d, because y is bounded between c and d, and then the inside integration goes from one function of y to the other. Therefore, our differentials are dx dy for a type 2 region, whereas they were dy dx for a type 1. And then for the type 3 region that we have on the right, we could set up either form of this. Let's look at some examples. It's not always going to be clear what type you're looking at, but first let's start with the type 1 region. So I would like to compute this double integral from 0 to 1, 0 to x cubed, 3 dy dx. The integral is already set up for us, but let's understand what we're doing. Our bounds indicate that 0 is less than or equal to x is less than or equal to 1, and 0 is less than or equal to y is less than or equal to x cubed. So now we would like to sketch the region in the xy plane that matches these inequalities. That's the region D that we're integrating over. So what I typically do is go ahead and do my constant bounds first. So our region of integration is somewhere between these two vertical lines, the y-axis and the vertical line x equals 1. Y is greater than or equal to 0, so our lower curve for y is the x-axis, and our upper curve for y is y equals x cubed. So the region enclosed is this region here. This is actually also a type 3 region. Or in other words, it's also a type 2 region. So we could have set this up differently, but the way the integral was given to us, it was set up as a type 1 region. So what we're going to do is take the integrand 3 and anti-differentiate with respect to y first. So we get this as the integral from 0 to 1 of 3y, and then we're going to evaluate it at y equals x cubed and y equals 0. So that's going to leave us with 3x cubed minus 0. And now we anti-differentiate this with respect to x, and we get 3/4 x to the 4th power, and then we need to evaluate this at 0 and 1. So the actual integration here is not too bad. Okay, let's look at this example. We would like to sketch the domain of integration and compute the double integral of xy over d, where d is the set of points in the xy plane for which y is less than or equal to x is less than or equal to 2y plus 1, and negative 1 is less than or equal to y is less than or equal to 3. So let's graph this region, and then we will set up our integral, anti-differentiate, and solve. Okay, so y is bounded between negative 1 and 3. Let me go ahead and place those horizontal lines on this graph. So our domain lives between these two horizontal lines. Now we need to place the bounds for x. For x, the left bound is the line y equals x, and the right bound is x equals 2y plus 1. If you prefer, you can solve for y in that equation just to have y equals mx plus b form. You would get y equals 1/2 x minus 1/2. We could go ahead and plot these lines, but I would first like to see what the x values are when y equals negative 1 and 3. When y equals negative 1, x is negative 2 plus 1, so x is negative 1. Then when y is 3, x is 6 plus 1, so x is 7. Okay, so that's our line x equals 2y plus 1. Okay, so this picture is not super drawn to scale, but let's look at the other one, y equals x. When y is 3, x is 3. And when y is negative 1, x is also negative 1. Okay, I moved those terms around a little bit just so the picture would be a little bit better, but there are the two lines. So the one on the left is y equals x. The one on the right is x equals 2y plus 1. The region they enclose between negative 1 and 3 is our domain of integration. Okay, so the integral we're going to set up is going to have y constant bounds on the outside. So our outside bounds are from negative 1 to 3. The inside bounds are from y to 2y plus 1. And then our integrand is xy. And then with the type of region we have, we're going to integrate first with respect to x, then with respect to y. So this is dx dy. We anti-differentiate with respect to x, and we're going to get the integral from negative 1 to 3 of 1/2 x squared y. And then our bounds for x were from x equals y to x equals 2y plus 1 dy. Let me take this just one step further. So we would have 1/2 times the quantity 2y plus 1 squared times y minus 1/2 times y cubed. At this point, it's just a single integral, so I'll leave it there. You would just anti-differentiate with respect to y, then plug in the bounds. Sometimes it's advantageous to take an integral which is written as dx dy and integrate it as dy dx if it's possible, or vice versa. This is called reversing the order of integration. We already saw from Fubini's theorem that over a rectangular domain, you can always reverse the order of integration. So if I want to integrate from a to b, integrate from c to d, f of x and y dy dx, over a rectangle, all we do is switch the outer bounds and switch the differentials. So we can say this is the integral from d to c, the integral from a to b, f of x and y dx dy. What about over a general region? Can I switch the order of integration? And the answer is yes, if you can describe the region both ways. In other words, if it's a type 3 region. So you have to be able to reverse the roles of the variables. Let's do this example. We would like to compute the integral from 0 to 2, the integral from x squared to 2x of the integrand 2x plus 1 dy dx by first changing the order of integration. I'm not actually going to compute it, I'm just going to set up what the new integral would look like. It would be an integral of the form dx dy. Let's sketch the domain of integration and conclude, ideally, that it's a type 3 region. Okay, x is bounded between 0 and 2. Y is bounded between x squared and 2x. So for x squared, when x equals 0, y equals 0. So we're going to pass through the origin for that first curve. And when x equals 2, y equals 4. So the parabola looks like this. And then y equals 2x also passes through the origin. And when x equals 2, y is 2 times 2, so y is also 4. So we have the same endpoints. Y equals 2x looks like this. So our domain of integration is this little sliver enclosed between this parabola and the straight line. This is a type 3 region. We can say that y values are bounded between 0 and 4, and then x is going to travel from the line on the left to the parabola on the right. So my new bounds are going to be 0 is less than or equal to y is less than or equal to 4. And then you imagine you fix a y value between those two bounds, travel left to right. We enter the region when x equals y over 2, and we exit the region when x equals the square root of y. So the line gives us our lower bound for x, and the parabola gives us our upper bound for x. So you travel left to right. So we could compute the exact same double integral, reversing the bounds, integrating from 0 to 4, integrating from y over 2 to the square root of y, 2x plus 1, so the integrand doesn't change, dx dy. And then you would just anti-differentiate and plug in your bounds in the usual way. Notice this is not just swapping the integral symbols on the left and swapping the differentials. This doesn't make any sense because our volume computation should be a number. But the outside bounds here are going to give us like a function of x or something like that. This is just completely wrong. Your outside bounds need to be numbers. Let's set up a double integral that represents the volume of the solid pictured below. That's the solid bounded by the cylinder y squared plus z squared equals 4, and the planes x equals 2y, x equals 0, z equals 0 in the first octant. I've given you the picture of the solid whose volume we would like to compute. Let's go through and identify these bounds. So y squared plus z squared equals 4 is a circular cylinder of radius 2 around the x-axis. So here's the x-axis, y-axis, and z-axis. So this rounded roof on our solid is part of the cylinder y squared plus z squared equals 4. The plane x equals 2y is going to be a plane that sits directly above the line x equals 2y in the xy plane because z is arbitrary. So we imagine taking that line and just stretching it up and down. So that's here. X equals 0 is the yz plane. So that's giving us the back wall to our solid. And then z equals 0 is the xy plane. And then we're also told that we're working in the first octant. So now we have all 4 edges bounding the cylinder. To compute this volume, what we're going to do is reinterpret this volume as enclosed between the graph of a surface and a region over the xy plane. So in particular, we're going to view this as volume enclosed between the graph of the function z equals the square root of 4 minus y squared and the region in the xy plane that's going to look like this triangular shape. I was able to deduce that that was a triangle just based off of the picture, but let's identify the edges now. One edge is the y-axis. The top side of the triangle is coming from this line in the xy plane, and that's the value y equals 2. That's where that cylinder of radius 2 intersects the xy plane. The line through the origin, of course, is x equals 2y, which means that this point up here is the point 4, 2. This is a type 3 region, so how about we set it up both ways? As a type 1 region, I'm going to say that x is bounded between 0 and 4, and y is bounded between x over 2 and the value 2. The function we're integrating is the square root of 4 minus y squared. And with this ordering, it's going to be dy dx. As a type 2 region, I can say that y is bounded between 0 and 2. And then if I come to any y value between 0 and 2 and travel left to right, we enter the region when x equals 0, and we exit the region when x equals 2y. So our x bounds are from 0 to 2y. Same integrand, but this time it's dx dy. So both of these expressions would compute the same volume. Let's conclude this lecture with some properties of integration. So the first property is the linearity property. And that is, if f and g are both integrable functions over d, where d doesn't have to be a rectangle, this could be type 1, type 2, etc. And if c and d are constants, they're scalars, then the integral of c times f plus d times g exists, and you can break this integral up over the addition and you can pull out the constants. So this would be c times the double integral of f plus d times the double integral of g. The second property is called monotonicity. And this says that if f is less than or equal to g, where again these are integrable functions over d, then the amount of volume enclosed under f is less than or equal to the amount of volume enclosed under g. So in other words, the double integral of f over d is less than or equal to the double integral of g over d. If d1 and d2 are two disjoint regions in the xy plane, so say these are my two regions, and you would like to integrate f over both of these regions, we can denote that as the double integral of f over the union of these regions. Then that's just equal to the double integral of f over d1 plus the double integral of f over d2. For the fourth property, I need to add a hypothesis that f is greater than or equal to 0. Here, if S is a subset of the region D, which we can picture like this, then the double integral of f, a non-negative function, over S is less than or equal to the double integral of f over d because we're going to be enclosing less volume. And then the final property here is really useful. This says that if your function f of x and y can be put in a factored form that looks like a function of x times a function of y. For example, f of x and y equals e to the x times cosine y. If you would like to compute the double integral of f over a rectangular domain, you can basically take that double integral and split it into a product for the x component and the y component. So we can write the double integral of g of x h of y over this rectangular domain as the product of the integral from a to b of g of x dx times the integral from c to d of h of y dy. Okay, we've reached the end of this lecture on double integration. Thank you for your attention.